Indian Economic Service 2025, General Economics 1, Section C, Question 10, Part C. We will construct the compensated demand function from the given utility function. Let's begin. So, the expenditure minimization problem is given as Lagrange L is equal to P1 Q1 plus P2 Q2 plus lambda of U bar, which is a given level of utility, Q1 alpha Q2 del Lagrange upon del Q1 is equal to P1 plus lambda times minus alpha Q1 alpha minus 1 times Q2 del Lagrange by del Q2 is equal to P2 plus lambda. What remains inside is minus of Q1 alpha. Put this equal to 0. Similarly for the first one. And the third first order condition is that of the constraint, which is simply U bar minus Q1 alpha Q2, which is equal to 0 again. Now solve for these three. Divide equation 1 by 2. So divide these two and we will get P1 upon P2 is equal to lambda alpha Q1 alpha minus 1 Q2 whole divided by lambda Q1 alpha. Lambda will cancel out and alpha will remain. For Q1, we have Q1 in the numerator as well as the denominator. So we'll put it in the denominator as alpha minus 1, which leaves us with just 1. That means P1 by P2 is equal to alpha Q2 by Q1. This is very similar to your traditional equation of price ratio is equal to MRS. But in the exam, it would have been better if you show the Lagrangian derivation. But essentially the result is the same, that is MRS is equal to price ratio. Now that we have Q1, Q2 in terms of P1, P2, let's take out Q2. Q2 comes out to be P1, Q1 upon P2 into alpha. Replace this Q2 in the utility function. So the utility function looks like Q1 alpha Q2. In place of Q2 we have the above expression P1 Q1 upon P2 upon alpha. This comes out to be U is equal to Q1 to the power alpha plus 1 into P1 by P2 will remain as is, and similarly 1 upon alpha. Write this entire expression in terms of Q1. You will get U into P2 by P1 into alpha, the entire thing raised to the power 1 upon alpha plus 1. This is the same alpha plus 1 that we received here. That's why it comes as 1 divided by alpha plus 1 in the power. Now we have the compensated demand function for the first commodity. That's denoted here. You can see the compensated demand function is a function of utility and prices, unlike the Marshallian demand function, which is a function of prices and income. Now we derive the demand function for the second good. You remember we had this expression Q2 is equal to P1 Q1 upon P2 alpha. So Q2 is equal to P1 Q1 upon P2 alpha. we have the value of Q1H. So to calculate Q2H, we'll use the value of Q1H. Q2H, which is the Hicksian demand function for the second good, is given as P1 by P2 into 1 upon alpha. All of this is as it is. Now we replace the value of Q1H that we calculated above. It comes out to be U P2 by P1 alpha whole raised to power 1 upon alpha plus 1. We need to refine this further because we have P1 upon P2 here, P1 upon P2 is also here, alpha is here, another alpha is here. So we'll get these terms into one side. Keeping the terms that are common together, U is raised to power 1 upon alpha plus 1. We don't need to touch this. Alpha is raised to power 1 upon alpha plus 1 and it is also divided by alpha. Similarly, P2 upon P1 is raised to the power of 1 upon alpha plus 1 and we also have P2 upon P1 here, but it will come in the denominator. Let's calculate 1 upon alpha plus 1 minus 1 because this is an expression that is used here as well as here. If you look closely, this is nothing but alpha raised to power 1 upon alpha plus 1 minus 1. This expression. Similarly for P2 by P1. So I'll calculate this one separately. We'll get 1 upon alpha plus 1 minus alpha minus 1, which is equal to 1 will get cancelled out, which is equal to minus alpha upon alpha plus 1. We'll use this in the terms above. So you'll get U, this one stays as it is, alpha plus 1. Alpha to the power 1 upon alpha plus 1 minus 1 gives us alpha to the power minus alpha upon alpha plus 1. And P2 upon P1 whole to the power minus alpha upon alpha plus 1. We can take alpha plus 1 as the common power. We'll be left with utility U alpha to the power minus alpha, P2 by P1, this also raised to the power minus alpha, and this entire thing raised to the power 1 upon alpha plus 1. This is your compensated demand function for the second commodity. We will calculate the expenditure function now. The expenditure function you remember from above is P1 Q1 plus P2 Q2. We will insert the values of the compensated demands for the first and the second commodity. The expenditure function consequently comes out to be P1. Q1H is given by U P2 upon P1 alpha, U P2 upon P1 alpha whole to the power 1 upon alpha plus 1 plus P2, put U alpha, this is raised to power minus alpha, P2 upon P1 is also raised to the power minus alpha, and this entire thing is raised to the power 1 upon alpha plus 1. You can solve the expenditure function further by getting common terms together, P1, P1, and consider the power that's here. Similarly, P2 is here, P2 is also here, and then we can further simplify this expression. This can be done at your end. It's simple mathematics. Let's talk about interpretation of the shape of the compensated demand curves, because that's another thing which the question asks us. So the compensated demand curves are downward sloping in their own prices. Let's see how. So Q1h, which is the compensated demand curve for the first commodity, you note that the price of the first commodity is in the denominator. So as you increase the price, the quantity demanded falls. This reflects the substitution effect, because substitution effect is the only effect that is present in the compensated demand curve. The compensated demand curve is devoid of the income effect. Hence, this is a clear inverse relation. Let's see what we have for the compensated demand of the second commodity. An inverse relation between the second good and its price. So while P2 is in the numerator, note that its power is negative, which essentially means that P2 will be in the denominator. That means when price of the second good increases, the quantity demanded falls, which again reflects substitution effect. Hence, the demand curve would be a normal downward sloping,